So let me start with this. I didn't have any chance to the preload the dice, so I don't know what question test student will be getting. Let's hope it's not one of the questions that I've already gotten before. And so I'm gonna start the timer, and once I start the timer, only 20 minutes. I think I mentioned this in my previous classes. It's a really short amount of time. Even I do struggle to finish everything in 20 minutes. I'll do my best. And if I get the same question, so that's the two lenses setup, generic setup question, then I'm gonna just reset the attempt with my instructor access and just do it again. At some point, I'll get the question that I haven't done before. So let's start. All right, that's a new question. So let's do that. Okay, you are trying to build a telescope. Okay, I see that. Okay, two converging lenses. Enter text answer. These numbers might not be randomized. I should have randomized it. Describe the arrangement. So let me just draw the picture because I think I remember from, well, I remember it from somewhere. You might remember it from lab. So if you have an optical axis, and let's imagine you have your objective lens here of some long focal length, like 150 centimeter. Then the way you would have to set up is so that the focal point of the both lenses are overlapping. So with another converging lens as the eyepiece, the eyepiece would need to be somewhere here with its focal point at 15 centimeters away, kind of overlapping. That's how you need to set up. That way, if you got some sort of you got parallel light kind of object from far away, it'll focus here at the focal point of objective, and the eyepiece will be at just the right place to form a virtual image at an infinity distance away. Something like that. Can't draw. Something like that. Something like that. Okay, close enough. So with that drawing in mind, I'm going to describe it here. So the two lenses should be separated by 165 centimeters so that the focal points of the two lenses are overlapping. Let's see. Extend the work, include the diagram. Okay, I think, and I can explain so that the final virtual image of a faraway object will be formed far away, meaning it can be seen, it can be focused with relaxed eyes. So that's A. B. The setup above is for relaxed eyes. You decide to see if you can get a greater magnification if you decide to strain your eyes a little. First, you start adjusting L. Okay, you change the distance. So I think now you're going to be given a distance. So let's do that. So for part B, we have the same two lenses setup, but now what's different is instead of figuring out what their distance should be, now you've been told that the distance between them is 159 centimeters. L is equal to 159.4 centimeters. So it's shorter. Before it was a total of 165. Now it's 159.4. Okay, and what is it? Find the location of the final image relative to the eyepiece lens. Also describe the image. Okay, good. So so this is what you work through. So you analyze each lens one at a time. So here's a lens with 150 centimeter focal length, and you have some object DO that's approaching infinity. So you go through the analysis to see where the image will be. It'll be at the focal point, but let me just go through the analysis. So you use the thin lens equation, 1 over DO plus 1 over DI is equal to 1 over F1, or F objective. Then with DO going to infinity, this whole thing goes to 0, which means 1 over di goes to f object. So di image forms, a real image forms at the focal point. That's what we talked about up there, and that part doesn't change. The only thing that changes is how far away is the eyepiece. So now I'm gonna do the second step of the analysis. So having found the image here, that becomes now the object for the second step of the analysis. This is gonna be DO prime. It'll form some image somewhere. I think it's gonna be somewhere out there, virtual image. So let's write down the equations and see. Let me get rid of these, so I don't have to, or actually, never mind. I think I can scroll. It's not too much scrolling. So let's work out the second stage. So second stage, we are saying 1 over DO prime, whose number will work out from the numbers given, plus 1 over DI is equal to 1 over the focal length of the eyepiece. So solving this for DI should be 1 over focal length of the eyepiece minus 1 over DO prime. So I should figure out DO prime. So from the numbers given, DO prime is 9.4 centimeter. Okay, I think I have enough. The rest of the calculation I can do in Wolfram alpha. That's the quickest way to do it with a limited amount of time. 1 over the 15 centimeters, that was the focal length of the eyepiece, minus 1 over 9.4 centimeter, that was the object distance. Yeah, I think I'm gonna get a negative number. Let's see, minus 25. Oh, yeah, I could have guessed that, I guess, because this is a like textbook near point, 25 centimeters. So my answer, which I could have guessed if I thought through it a little bit better, is minus 25.2 centimeter. But I think in any case, even if you could guess it, you should still like derive it anyway, so it's fine. So final image is 25.22 centimeter away from the eyepiece, on the opposite side from the outgoing light waves. Virtual image. So it's a virtual, and I think it's going to be it'll be an inverted image. And if we want to justify why it would be inverted, you would be working through the total magnification, which is going to be equal to magnification of the objective times the magnification of the eyepiece. And when you work out magnification of the objective, which is equal to minus di over do, that's going to be negative because both the do and di are positive. So you start out with a minus inverted image here, and when you do the eyepiece, because your object distance is positive, image distance is negative, the magnification will be positive. So minus times plus, your total magnification is minus, meaning inverted image. Yeah, so that's B. What is the total angular magnification of your setup in B above? Oh yeah. So you gotta work through that. Do I have enough time? Got 10 minutes at least? Okay. So I think the easiest thing to do is figure out the angular size of the thing. So, it says you may assume that you are looking at that. Okay. So, okay, let's follow the hint. It says start with the definition of angular magnification, which is going to be the theta of the final image divided by theta reference. And here, because it's a telescope, theta reference will be basically given by there, 2 meters tall divided by, that's 2 meters tall divided by the distance 1 kilometer away. That kind of gives you the angular size of things at small angles. I don't have to bother with the arcsine, arctangent when it's a small angle. So for theta image, that's where now I should work through. So I already worked out the image distance. If I work out the final image height, then I can do the, for the theta image, I can do the image height, height of the image divided by this image distance di. That'll give me the image angular size. So let me actually copy and paste this expression that I was writing. Because so to figure out the image height, you need a linear magnification. So let's start there. Your linear magnification was that. So I think I need to figure out the, and it kind of helps me that the question is letting me use some actual distance of the object, because otherwise I think my the linear magnification expression for objective lens minus di over do, if do is infinity, di is like you get something that's a zero. I don't want to deal with the zeros, so it's gonna be minus. I think I can keep the di as being basically the focal length of objective, and do instead of being infinity, it'll be 1 kilometer. So I can get some numerical value for magnification of objective lens. And then magnification of the eyepiece will be minus di prime over do prime. And I think I had a do prime number. So this, let me just type in the, put in the numbers from above. Image distance was 25.2 centimeter. Object distance was 9.4 centimeter. 9.4 centimeter. And let me forget the minus signs. I'm just dealing with the absolute numbers. So let me work out the number above there. That's gonna be objective 150 centimeter divided by 1 kilometer. That'll give me some number 0.0015, and let me do that times this ratio. That'll give me total magnification times 25.2 centimeter divided by 9.4 centimeter. So with that total being equal to 0.00402, I can get the height of the final image as m total times the height of the object. So I already have m total there. I just need to multiply the height of the object 2 meters. So that times 2 meters. And it's going to be smaller than 2 meters, I think. It'll be, 0.804 centimeter. That doesn't mean it has a less than 1 angular magnification, because we have to go through this final calculation. So, so let me use height of the image of 0.804 centimeter. And the image distance, this is the part that gives you the angular magnification. Image distance is 25.2 centimeters. So the theta image will be, I guess I can actually use this number. All of this divided by 25.2 centimeters. So that's the angular size of the image. So take that, divided by the reference angular size. So take all of this divided by 2 meters divided by 1 kilometer. That'll give you the angular magnification, and you get 16. Okay, so I'm gonna put in 16. So m is equal to 16. Is that good or bad? I can't tell. Let's see, 60 minutes. So in the ideal setup, your angular magnification must have been 10, the ratio of the two focal lengths. So from 10 to 16. Oh yeah, I think that is better. Yeah. work attached. And for the work, I'll attach this and this page because I think that basically contains all the numbers that I'm putting in. So yeah, and in this number you can kind of see how 1 kilometer would have canceled out. So if an object is actually infinite away, that's actually fine. It'll have canceled out. It's just that earlier when you're plugging numbers, that's in the way. So yeah, with the strain die, I guess angular magnification is better. Yeah, good. As you look at a friend 1 kilometer away, you ponder the question: what is the smallest thing you can see? Yeah. So the additional information you need is the main information I need is the aperture size of the telescope in order to apply the Rayleigh criterion, which is I always forget this. So theta mean is equal to 1.22 times wavelength divided by aperture. I think that's correct. I forget where 1.22 goes. Oddly enough, I remember the number itself. For the wavelength itself, we can reasonably assume it's around 500 nanometer for visible light. All right, I think yeah, I don't think I'm being asked the actual angular resolution limit. So yeah, so that's my answer. Yeah, I guess I'm done. So I got 4 minutes, but I think I did everything. I think there's a version of this question where it's not a converging lens but diverging lens that'll have its own consideration. One thing that I can say is still the same is the description I gave earlier, how for A you overlap the focal lengths. The way with the diverging lens it overlaps would change to where the lens is here. But for this diverging lens, you consider, you have focal point there. So that's what's overlapping. So that part, the description that the focal points are overlapping, that still remains the same when you do the diverging lens. Just have to be careful on which side you place it. So, okay, I think that's everything. Let me just attach work and submit. And I might check the answer key just to make sure that I didn't make mistakes. I don't know. I have made mistakes in the timed assessment before, both from combination of the time pressure, me hurrying and forgetting something, and I think the freeform timed assessments, they are complex questions. I would say I make mistakes with these at a higher rate than I would do with the run-of-the-mill homework questions. So let's see here. Oh, yeah. And then I'll say remaining calculation done in Wolfram Alpha, screenshot below. Right, so that's everything. Let me submit it. Go in with the instructor access to double check that I got the correct. I want to mainly double check that this answer 16 is right. Because there's a chance I made a mistake somewhere. I don't know. Submit and I did put a lot of care into coding in the answer key, so what's in the answer key should be right. So with that, now when you do review work, you will see a screen where you can change your work. If you want to change your work, which you can, my instruction to you is, organize it, make sure it's presentable. Just to refresh this screen, then you will get this view where you add the work button where you can actually change your work. You can change the answer key, but if you discover a mistake or something, you can change your attached work. The system will timestamp when you last changed it. I usually don't pay attention to that unless you are attaching your work after I've graded it, which could be some time ago, sometime later. So okay, so let me just check the. Oh, or I think with the answer key, I'm happy displaying it on screen for the questions I'm doing. Let me just navigate to the right question with the test student work instead of anyone else's work. So this is the test student work being viewed under instructor access. Let's see here. Wait, did it ask for? Oh, it did ask for angular magnification. I forgot to give it. Oh, oops. Yeah, you should give it. I did say it out loud that it's gonna be 10. Yeah. All right. Setup is for relaxed eyes. Final. Yeah. 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 Is 25.18 or 2. Yeah. Good. And here, let's hope 16. Okay, good. Correct. Yeah. Yeah, yeah. At least with, I think you if you get the diverging lens version, this is I found that it's less with the diverging lens. Yeah, I wouldn't have guessed it. I would have guessed that with the both types, somehow if it's a strained, you'd get bigger image, but with the diverging lens, you get smaller magnification. And here, yeah, I think that's basically it. Yeah. Good. So I don't think I made any mistakes here. So that's this question.